In Chapter 13, we're going to deal with the concept of equilibrium in the context of chemical reactions. We're going to introduce reaction rates and collision theory, what is actually happening during a chemical reaction molecularly, talk about chemical equilibrium and equilibrium constants, learn how to write them, and then follow up with factors that affect equilibrium, then introduce the concept of buffers to tie in acid-base chemistry, the chapter that we just finished, and the factors that affect equilibrium as well. First of all, let's talk about reaction rates. Well, rate of anything refers to how fast something is happening, the speed. So if I'm talking about the rate of a reaction, that simply means how fast the reaction is occurring. Reactions have different rates. Some happen very quickly, some do not. And therefore, that tells us that it's a reaction that proceeds faster. Those molecules are colliding and forming products much quicker than a different reaction. This is important in industry because to make something efficient, we would like to speed up the rate of a reaction to make it efficient and worthwhile for industry, right? Now let's take a look at what is happening during a chemical reaction. We base all of this on the collision theory, which first of all tells us that obviously for a reaction to occur, these reactant particles have to collide with each other. And that's when chemical reactions happen. Now, these particles can be atoms, molecules, ions, whatever form, but the chemical reaction will happen when they collide with each other. Here's a look at what is happening to the energy of this reaction as the reaction proceeds, right? So at time 0 here, I have nothing. I just introduce my reactants, which have a certain amount of energy associated with them. As the reaction proceeds, we get this shape, this curve, that tells us something about what is happening. If my reactants are here, then my products are over here. Now, I don't proceed directly from reactants down to product, to the energy of the product. There's actually a little bit of a hill that I have to climb as a reactant to get to the place where all I have to do is kind of roll down and get to forming the products. The height of this hill here from the energy of my reactants to the top, this is called the activation energy, and it's the amount of energy that it's needed to initiate the reaction, to get it going. Every reaction has some sort of activation energy that is associated with it. For some, this activation energy is very large. For some other reactions, it's very small. And we will talk about what affects this as well. There's one thing that really affects it, and we'll talk about it. Note the difference between these two curves. Here, my products are lower in energy than my reactants. This is an exothermic reaction, whereas here, my products are higher in energy than my reactants, and this is really an endothermic reaction. So this is an illustration of an endothermic reaction. I want you to remember, though, that all reactions have some sort of activation energy that is needed to initiate the reaction. So let's take a look at what is happening during this curve with the molecules. So if I have this molecule or this atom and this molecule, if you will, and this is before collision, what happens when they collide at a certain orientation with a certain energy? Well, then what I have is the transfer of this molecule to the atom forming a different molecule, leaving behind part of this molecule that was the reactant, right? It's a different one now. So what I have here is my products, and here I have my reactants, and they collide with each other with enough energy to cause this reaction to occur. Here at the beginning, I have my reactants. So I have just the atom and I have this molecule. Down to the product side, I have the two new molecules that were formed. Up at the top, however, I have a combination of those molecules, those reactant molecules. And this reaction can either proceed to products or it can go back to the reactants. If it doesn't have enough energy to go over this hump, it will just roll back down to the reactants where I started. So here's an example of that. Here's before my collision. They collide, but they don't collide with enough energy like here. And you can see that with this bright yellow. It's stronger than this one here. These don't collide with enough energy, and therefore I don't have a reaction that is happening. So not all collisions between reactant molecules will end up forming products. So according to the collision theory, the rate of that reaction depends on the number of the collisions. So how many collisions do I have? And on the energy of those collisions. So how many of those reactant molecules that are colliding have enough energy to initiate the formation of products. What's not mentioned here but is also true is the orientation of those collisions, but we're not going to worry too much about that right now. So focus on how many collide and whether they have enough energy or not. The number of the collisions can be increased by just increasing the concentration of the reactants. So obviously, the more reactant molecules I have in the container, the more collisions I'm going to have. And that also, because I have a greater number of collisions overall, that's going to increase the number of collisions that have enough energy to continue to react and give me products. So one factor that uh, influences the rate of the reaction is the number of reactant collisions, so the concentration of my reactants. But the energy of those collisions is another way to increase the rate of the reaction. And how do I increase the energy of the collisions? I increase the energy of the molecules themselves. And how do I do that? Well, we talked about the kinetic energy of the molecules that is dependent on the temperature. So if I increase the temperature at which the reaction takes place, then molecules are going to move faster and have enough energy to initiate a reaction.